Pokok bahasan kita ya, termokimia. Termokimia itu secara harfiah sebetulnya termo itu panas dan kimia itu adalah ya energi kimia ya, senyawa kimia. Jadi kurang lebih itu ilmu yang mempelajari tentang kaitan antara energi panas dan energi yang dimiliki oleh senyawa kimia tersebut. Kalau kita menggunakan kendaraan ya yang diisi dengan bahan bakar BBM, bahan bakar minyak, itu panasnya yang kemudian dipakai untuk menggerakkan kendaraan kita. Kemudian jadi misalnya kalau di mobil saya itu saya lihat terakhir digunakan hari Jumat kemarin, itu setiap 1 liter bensin itu digunakan untuk menempuh jarak sekitar 11,1 liter, 11,1 kilometer. Berarti setiap perjalanan saya 11,1 kilometer, saya menghabiskan bahan bakar minyak sebesar 1 liter. Nah, itu berarti energi kimia yang ada dari senyawa hidrokarbon penyusun bahan bakar minyak itu digunakan untuk menggerakkan mobil. Nah, analogi ini bisa dipakai juga untuk misalnya menggunakan kendaraan bermotor atau yang menggunakan jenis kendaraan lain. Misalnya yang naik kereta ya, di situ kan kita bisa memperkirakan berapa besaran energi yang dipakai untuk misalnya mengangkut gerbong. Semua itu tentu bisa kita hitung. Nah, energi ini entalpi atau energi panas ini sering dilamakan dengan H sebagai simbol dari kata heat ya, panas. Nah, tetapi sebagai H ini sebetulnya dia tidak bisa diukur secara absolut. Jadi umumnya dia diukur secara relatif, artinya dibandingkan dengan ada benchmark ya, ada pembanding yang dianggap standar dan selalu merujuk pengukuran pada pengukuran standar tersebut. Nah, kemudian karena H itu sifatnya tidak absolut, maka sebetulnya lebih penting itu untuk mengukur delta H atau perubahan entalpi dibandingkan dengan mengukur H. Oke. Kita lihat dulu video ya. Ini nggak ada suaranya, pada tidur apa?
Ada,
Halo?
Bu. Ada, Bu.
Ada. Kirain udah pules. Oke, kita lihat dulu video pertama ya.
So guys, I was talking about enthalpy in some videos and I'm sorry I haven't introduced it properly. It is now time to introduce it formally, and I love it because it's nothing complicated on the explanation, but understanding it and how to apply it, I think it might confuse you a little bit. Essentially, it's a mathematical value, H equals internal energy plus PV value. And probably you're wondering what is this PV value? And we have it a lot on open systems. Let's say that you could calculate enthalpy of many open systems if you had the internal energy and the PV value, which is essentially, for example, I like to call it, you have this open system, the push energy, you have volume, yes, you have pressure, yes. So you have a flow energy here and a flow energy going out. And even though you're heating here, you know that this stuff is moving. So who's doing that work? That work comes from the PV value, or at least I like to call it like that. So I get an idea. So I got internal value, which is totally dependent on temperature, and the PV value, which is dependent on other, let's say, other things. Actually, if I were to tell you, no, enthalpy, the letter H, has no value at all, has no physical value, but it's a very important abstract concept that will help us to model open systems in general, and even closed systems will help us as well. But essentially, we have enthalpy for open systems. So you can say that enthalpy is more or less the equivalent to internal energy. This is for open systems, and this is for closed systems. In general, guys, please don't make the generalization, but it will help you to understand more or less why do we need this value here. Now, why are we speaking about enthalpy? Because we're going to find it a lot in tables and diagrams. Actually, I told you pressure enthalpy diagram. And what's enthalpy? Essentially, enthalpy is energy. Many times heat energy, many times work energy. Enthalpy can be, let's say, calculated with either heat, work, or even kinetic energy, even potential energy can be transferred or exchanged to form enthalpy. So for now, just know that it is a very important variable. We will see it and study a lot in the first law, actually, well, a little bit when we're concluding on this section, but the first law is, I think, the most easy to get, and we will, of course, use a lot of exercises, and you will get the idea. Enthalpy, I wanted to tell you that is extensive value, that this depends on the amount of mass, of course. You have more mass, you will have more energy, makes sense. And enthalpy, very important, is a state function. It does not depend on the path. So if you have, I don't know, if you increase this ball, this height, well, you will have an energy. If you decrease this, you will not have that energy, of course. So it's like internal energy is similar, very similar. You can compare them, and yeah, essentially it's everything I wanted to show you. One last thing is, when calculating absolute enthalpies, this is very hard. Don't do it. We're more interested in the changes or deltas. Probably if I tell you, okay, this particle is moving, vibrating at 0 Celsius. Well, why would if I'm only interested in changing this particle from this state to 5 Celsius, why will I want to calculate how much enthalpy is needed to move it? Why not use the reference? I have this 0 Celsius, will be now my 0 enthalpy, and I can actually measure this change. Yes, I can. And when I get to 5, I will get a final enthalpy, which is, I don't know, maybe 10 joules, and I will get the difference value, the change value, which is enough, because many times we will get heat as a change of enthalpy or work as a change on enthalpy. And even though you cannot calculate H2 absolutely or H1 absolutely, you can calculate the difference. So essentially, that's what I wanted to tell you on enthalpy, guys.
ini dari kawan-kawan semua bebas. Jikalau nantinya mau pasukan tentara.
Oke, nah sudah dulu tadi video pertama. Jadi penjelasannya bahwa entalpi itu tadi ya konsepnya tidak absolut. Jadi yang lebih penting itu adalah mengamati delta H-nya atau perubahan entalpi. Dan entalpi itu kalau berdasarkan persamaan dibuat dalam H sama dengan U plus P kali V. U itu merupakan energi internal ya, energi dalam. Kalau pada sistem terbuka yang tidak yang tidak berubah tekanan dan volumenya, maka secara umum entalpi itu sama dengan energi dalam. Nah, kalau tadi contohnya misalnya kalau energi dalam itu pada closed system, maka kalau entalpi itu lebih pada open system. Kemudian lagi yang bisa di-highlight tadi. Entalpi itu bisa dimanifestasikan dalam konsep energi, kalor, atau beberapa work, E, Q ya, yang bisa dianggap sebagai wujud atau bentuk dari entalpi. Saya lanjutkan ke PowerPoint-nya lagi ya. Nah, ada yang dikenal dengan reaksi eksotermis. Reaksi eksotermis itu entalpi reaksinya atau perubahan entalpi reaksinya, delta H minusnya. Delta H-nya itu dilambangkan dengan negatif. Negatif ini bukan berarti nilainya di bawah 0 ya, tetapi negatif ini menunjukkan bahwa sistem itu melepaskan energi ke lingkungan, hingga diberi tanda negatif. Atau melepaskan panas ya sebesar nilai kalor tertentu. Kemudian ada reaksi eksoterm, ada reaksi endoterm, yakni yang menandakan menyerap panas sebesar delta H, yang menunjukkan bahwa kalau nilainya positif itu artinya sistem itu menyerap energi. Gambarannya kurang lebih seperti ini misalnya. Kalau kita menggunakan rice cooker ya untuk memasak atau apapun lah kompor listrik yang tertutup, maka energi listrik itu menjadi sumber yang memberikan panasnya atau memberikan kalornya ke dalam sistem. Sistemnya ini adalah wadah tempat kita memasak tadi ya, seperti rice cooker. Nah, pada ketika misalnya temperatur sudah naik, yang dimasak sudah matang ya, maka ada beberapa bagian itu yang akan terasa hangat. Itu artinya sistem melepaskan energi yang ke lingkungannya. Itu mungkin yang tertutup ya. Tapi misalnya yang terbuka, kalau misalnya kita menaruh wajan atau dandang ya, panci di atas kompor. Nah, maka kalau kita anggap sebagai sistem, panci itu wajan menerima panas dari tabung gas misalnya atau listrik kalau kita menggunakan kompor listrik, dan ketika misalnya kita menggunakannya untuk memasak dan ketika temperatur sudah naik, maka wajan atau panci tersebut akan melepaskan panas yang terasa ya. Itu artinya panas dari tabung gas atau dari kompor listrik itu memberikan panas secara endoterm ke dalam sistem, kemudian sistem melepaskan lagi ke lingkungan yang di luar. Hingga kita bisa tahu bahwa misalnya kondisinya sudah matang atau sudah bisa dikonsumsi. Itu, nah ini 1 kalori itu kurang lebih setara dengan 4,186 Joule atau biasa kita kenal dengan 4,2 Joule. Itu konversi ya. Oke. Sampai sini ada pertanyaan?
Tidak ada, Bu, bisa dilanjutkan.
Oke. Selanjutnya dengan video yang kedua ya.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released. But it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define. But a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Nggak tahu itu profesor beneran atau enggak ya. Tapi yang dia sampaikan itu betul adanya, sederhana dan gampang dimengerti. Jadi kalau ini menegaskan penjelasan sebelumnya, kalau isoterm itu artinya melepaskan panas ya ke dalam dari sistem ke lingkungan. Kalau endoterm itu dari lingkungan memberikan energinya ke dalam sistem. Tadi kalau dia kasih contoh, misalnya metana itu dibakar maka menghasilkan kalori sekitar 809 kilokalori per joule ya. Kilokalori per mol. Nah, jadi kalau misalnya tiap membakar 1 mol metana dapatnya segitu. Kalau kita membakar 2 mol metana dapatnya berarti 2 kali. Jadi semakin besar volumenya, semakin besar jumlah molnya, semakin besar masanya, itu bisa membuat energinya juga semakin meningkat. Ini bisa kita analogikan dengan ya tadi kalau misalnya kita mengisi bahan bakar 2 liter, kalau 1 liter misalnya bisa 11,1 kilometer jarak tempuhnya. Tapi kalau saya mengisi 2 liter berarti jarak tempuh kendaraan itu bisa sampai 22,2 liter. Nah, tadi juga dia sebutkan jangan confusing dengan kalau yang di makanan. Kalau di makanan itu menggunakan C-nya C besar, kalori, yang biasa disingkat dengan kakal, kilokalori. Nah, itu biasa kita lihat di kemasan makanan ya. Walaupun sebetulnya secara harfiah juga makanan itu sebetulnya energi kimia ya, yang kita pakai untuk aktivitas fisik kita sehari-hari, untuk berpikir, untuk bergerak, melakukan mobilitas, dan hal-hal lain yang memang kita perlukan untuk aktivitas sehari-hari. Tapi maksudnya kalori yang dimasukkan dengan energi kimia secara sederhana tadi itu satuannya berbeda dengan kalau kita menyebutkan yang dalam makanan atau kilokalori. Oke, saya lanjutkan dengan ini ada 3 jenis entalpi reaksi, yakni yang pertama ada delta H pembentukan, yakni panas yang dikeluarkan. Nah, ini kalau dikeluarkan berarti dia eksotermis, atau panas yang diperlukan atau yang disebut dengan endotermis untuk membentuk 1 mol senyawa dari unsur-unsurnya. Nah, itu kalau dia pembentukan. Kalau delta H penguraian, yaitu panas yang dikeluarkan, ini juga kalau konteksnya reaksi eksotermis atau diperlukan jika reaksinya endotermis untuk menguraikan 1 mol senyawa menjadi unsur-unsurnya. Yang ketiga itu delta H pembakaran, yakni panas yang diperlukan, panas yang dikeluarkan jika reaksinya eksotermis, atau panas yang diperlukan jika reaksinya endotermis untuk membakar 1 mol senyawa menjadi unsur-unsurnya. Oke, sampai sini ada pertanyaan? Ada yang mau ditanyakan? Belum? Cukup jelas. Oke, terima kasih Alif. Sekarang kita coba lihat video yang ketiga ya.
In this video, we're going to focus on thermochemistry and some of the equations that you need for this chapter. So let's begin. Let's start with internal energy. The change in the internal energy of a system is equal to Q plus W. Now, Q represents the amount of heat energy that enters or leaves the system. So here's a question for you. Let's say if inside the box represents the system, and let's say the outside, anything outside the box is the surroundings. Now let's say the temperature of the system is 100 degrees Celsius, but the surroundings is only 50 degrees Celsius. Well, actually, let's say 25. Now, will Q be positive or negative? Heat flows from hot to cold, so heat is going to flow out of the system into the surroundings. So Q relative to the system is going to be negative, excuse me. Q is negative. Whenever heat is released from the system, it's considered to be an exothermic process. Now for the surroundings absorb heat energy, so Q is positive for the surroundings. So it's endothermic for the surroundings. Anytime heat is absorbed, Q is positive. Typically, Q is measured in joules. Now you need to know that 1 kilojoule is equal to 1,000 joules. And a calorie, a lowercase calorie, that's 4.184 joules. A capital calorie is 1,000 lowercase calories. So those are some other conversion factors you need to know. W represents work, and work is equal to negative P delta V. When work is done on a system, W is positive. Whenever work is done on a system. Now, if work is done by the system, W is negative. Now, for this equation, W equals negative P delta V. When the change in volume is positive, whenever a gas expands, the work is negative due to this negative sign. And so whenever a gas expands, it can do work. It can exert a force to move a piston or something. Now, to compress a gas, you need to apply a force. So whenever gas is compressed, the change in volume is negative, so the work overall is positive. So as you apply a force to compress the gas, you're performing work on the system. So the internal energy of the system goes up whenever you do work on it. But whenever the system does work, or whenever work is done by the system, the internal energy of the system goes down. It loses potential energy because it's using up energy to do work. So let's see if we can apply this information in a practice problem. But before we do, another thing you need to know is that 101.3 joules is equal to 1 liter times 1 ATM. So now, let's say if 300 joules of heat energy was absorbed by the system, and also, let's say the system, which is a gas, let's say the gas expands from 2 liters to 3 liters at a pressure of 5 ATM. Calculate the change in the internal energy of the system. So the first thing we need to do is use this equation. W is equal to negative P delta V. The pressure is 5 ATM. The change in volume, final minus initial, it's 3 minus 2. So P delta V is going to be negative 5. And the units is going to be liters times ATM. Now, in order to get delta E, we need to convert liters times ATM into joules. And as you mentioned earlier, 1 liter times 1 ATM is equal to 101.3 joules. So the units, liters cancel, and ATM cancel as well. So what's 5 times 101.3? 5 times 100 is 500. 5 times 1 is 5. And 5 times 0.3. If 5 times 3 is 15, 5 times 0.3 is 1.5. So this is going to be negative 506.5 if you add 500 plus 5 plus 1.5. So that's how many joules of work that has been done by the system. So that's why W is negative, because the gas expanded and the gas performed work. So the internal energy of the system went down. So now we can calculate everything. Let's plug in what we have into the delta E equation. So since heat energy is absorbed, it's endothermic. Q is positive 300, and W is negative 506.5. So 300 minus 506.5, that's going to be equal to negative 206.5 joules. So that's how much energy the system lost overall. So now there's some other equations that you need to know. Q can be calculated using the equation mc delta T. M is the mass, C is the specific heat capacity, and in the case of water, it's 4.184 joules per gram per Celsius. So what this means is that if you have a 1 gram sample of water, it takes 4.18 joules to heat up that 1 gram sample of water by 1 degree Celsius. Delta T is the change in temperature, which could be in Kelvin or Celsius. So let's say if you want to calculate, the amount of energy that's required to heat up, let's say 50 grams of water from 25 degrees Celsius to 75 degrees Celsius. How much energy is required? So the mass is 50, the heat capacity of water is 4.184, and the change in temperature, final minus initial, 75 minus 25, that's 50. So if you have a calculator, 50 times 50 is 2,500, and if you multiply that by 4.184, you should get 10,460 joules. So that's how much heat energy is required to heat up 50 grams of water from 25 degrees Celsius to 75 degrees Celsius. And if you divide this by 1,000, you could convert your answer into kilojoules if you want to. So whenever you want to calculate the amount of heat energy absorbed or released whenever there's a temperature change, use the equation Q equals MCAT. Now, whenever you want to calculate the amount of heat energy that's absorbed or released whenever there's a phase change, you can use the equation Q equals M times delta H. This could be enthalpy of fusion or vaporization, or you can use Q, which is equal to N times delta H. It really depends on what the units of delta H is. And personally, I think it's easier if you just convert it. So let me give you an example. Let's say if you have 54 grams of ice at 0 degrees Celsius, and you want to find out how much heat energy is required to melt that ice into liquid water at the same temperature. Whenever you melt ice, while ice is melting into liquid water, the temperature, it remains constant. So this is a phase change. We want to go from a solid into a liquid. So it's easier if you simply convert it. Now you need to know the heat of fusion for water. The heat of fusion for water is about 6 kilojoules per mole. So what that means is that if you have 1 mole of water, you require 6 kilojoules to melt ice. It requires 6 kilojoules of heat energy to melt 1 mole of ice into liquid water. So what we need to do is convert grams to moles and then moles to kilojoules. So let's begin. So we have 54 grams of H2O in the solid form. And if you look at the periodic table, oxygen has an atomic mass of 16 and hydrogen has a mass of 1 times 2. So the molar mass for water is 18 grams per 1 mole. And so the units, grams, cancel. And now we can convert moles to kilojoules. We know that 6 kilojoules of heat is required per 1 mole of ice. So let's see what this is equal to. 54 divided by 18 is 3, and 3 times 6, well, that's going to be 18. So there's 18 kilojoules of heat energy that's required to melt 54 grams of ice into liquid water. Now, sometimes you might get what is known as a thermochemical equation. So consider the combustion reaction of propane with oxygen gas. It's going to produce CO2 and water. Go ahead and balance this reaction. And let's say this reaction releases 1200 kilojoules of heat energy. Notice that there's no delta H symbol. If you see the kilojoules of heat energy on the right side, it's exothermic. If you see it on the left side, it's endothermic. Now, whenever you want to balance a combustion reaction, balance the carbon atoms first. So let's put a 3 in front of CO2. Now, there's 8 hydrogen atoms on the left, so we need a 4 in front of water. And so we have 6 oxygens from the 3 CO2 molecules, 4 from H2O, 6 plus 4 is 10. If you divide it by this number 2, you're going to get 5. So we need to put a 5 in front of O2. So now this reaction is balanced. So how many kilojoules of heat energy will be released if 64 grams of oxygen reacts? How would you answer that question? How would you find the answer? So just like before, we're going to convert grams into moles and then moles into kilojoules. So let's start with 64 grams of oxygen. Let's convert it to moles. Anytime you want to go from grams to moles, you need to use the molar mass found in the periodic table. The atomic mass for oxygen is 16. So for O2, 16 times 2 is 32. So there's 32 grams of O2 per 1 mole of O2. And so as we can see, the units grams of O2 cancel. Now you need to understand what this number means. So if 1 mole of propane reacts, 1200 kilojoules of heat energy will be released. Now, if 5 moles of O2 reacts, 1200 kilojoules of heat energy will be released. If 3 moles of CO2 is produced, well, that's going to correspond to 1200 kilojoules. So what you need is the kilojoule per mole ratio. So since we're dealing with oxygen, the 5 is important to us. So for every 5 moles of O2 that reacts, 1200 kilojoules of heat energy will be released. And so we can eliminate moles of O2. So now we can do the math. So let's see if we can do this without a calculator. So 64 divided by 32 is 2. And so we have 2 times 1200 and a 5 on the bottom. So 1200 is basically 12 times 100. And 100 is 20 times 5. So we can cancel the 5s. So what's 20 times 2? 20 times 2 is 40. And now what's 40 times 12? Well, 4 times 12 is 120. So I take that back. 4 times 12 is 48. So 40 times 12 is 480. You can see it this way. 40 is 4 times 10. So if you multiply 10 and 12, you get 120. 120 times 4 is 480. So let's go back to this example. Now let's say if 3600 kilojoules of heat energy was released in this reaction, how many grams of CO2 was produced? So we want to go backwards. We want to convert kilojoules to moles and moles to CO2. So let's start with 3600 kilojoules. Now, the kilojoule per mole ratio is 1200 kilojoules for every 3 moles of CO2. So we're going to use that to go from kilojoules to moles. So for every 1200 kilojoules of heat energy that was released, 3 moles of carbon dioxide was produced. So the units kilojoules cancel. And now the last thing we need to do is convert moles to grams. So the molar mass for CO2 is going to be 12 for carbon plus 32 for the 2 oxygen atoms. So that's going to be 44 grams of CO2 per 1 mole. And so these units cancel. So 12 goes into 36 3 times. You can cancel the zeros if you want. So we have 3 times 3 times 44. So 3 times 3 is 9. So what's 9 times 44? 9 times 44 is basically 10 minus 1 times 44. So 44 times 10, that's 440. 44 times 1 is negative 44. So 440 minus 44, how much is that? So 440 minus 40 is 400. And if you subtract another 4 from that, you should get 396. And so there's going to be 396 grams of CO2 that's produced in this reaction. Consider this reaction. Methane reacts with oxygen gas to produce CO2 and water. And let's balance it. So we need a 2 in front of H2. We already have 1 carbon atom on both sides. Now we have 4 oxygen atoms on the right side, so we need a 2 in front of O2. So now, let's say if you're given the heats of formation for CO2, for H2O, and CH4. Let's say for CH4, it's negative 785. And this is delta H with an F on the bottom and a circle on top. That's the enthalpy of formation. The enthalpy of formation is the enthalpy of the heat that's absorbed or released, or the enthalpy of the reaction whenever a compound is produced from its elements in its natural standard state, and you have to produce only 1 mole of that compound. That's the definition for the enthalpy of formation, if you want to know, but we don't have to worry about that for this example. But let's say for CO2 it's about negative 393, and for water it's negative 286. How can you use this information to calculate or estimate the enthalpy of this entire reaction? If you want to find the enthalpy of the reaction using the heats of formation, it's the sum of the enthalpies for the products minus the sum of the heats of formation for the reactants. That's how you can calculate it. So on the product side, which is the stuff on the right side, we have CO2 plus 2H2O. And for the reactants, the reactants, that's the stuff on the left side. We have CH4 plus 2O2. Now the value for CO2, that's negative 393. And for H2O, it's going to be 2 times the value for H2O, which is negative 286. And then minus that for CH4, which is negative 785. Now O2 is a pure element in its natural state, so it's 0 for any such elements. So now we just got to do the math. So we have negative 393. 2 times 286, that's, I'm going to use a calculator for that. That's a negative 576, and negative 785, that's plus 785. So if you add these numbers up, you should get negative 184. So that's how you can estimate the enthalpy.
Itu sampai ke perhitungan energi ikatan sebetulnya. Nah, kita belum masuk sampai ke sana di minggu pertama. Saya lanjutkan sedikit di PowerPoint-nya. Nah ini ya, jadi kita akan mempelajari namanya hukum Laplace dan hukum Hess yang terkait dengan elektrokimia. Jadi kalau dalam hukum Laplace itu jumlah kalori yang dilepaskan dalam pembentukan satu senyawa itu akan sama dengan jumlah kalori yang diperlukan untuk menguraikan senyawa menjadi unsur-unsur. Sementara kalau hukum Hess itu jika perubahan kimia dibuat menjadi beberapa jalan atau cara yang berbeda, maka keseluruhan energi panas totalnya itu tetap. Jadi dia tidak bergantung pada jalan atau cara yang ditempuh. Nah, kalau hukum Laplace kita bisa langsung sebetulnya menganalogikan ya, kalau misalnya kalau untuk membentuk itu membutuhkan 100 kilokalori, maka untuk menguraikannya juga kurang lebih butuh 100 kilokalori. Nah, tapi kalau yang hukum Hess memang ini tergantung pada tingkatan reaksi. Berapa tahapan mekanisme reaksi yang dilalui untuk mencapai produk ya. Kalau misalnya walaupun misalnya ada 3 tahapan reaksi tapi produknya itu sama, maka kalau menurut hukum Hess harusnya total energinya itu sama. Mungkin bisa kita bayangkan kalau misalnya kita mau mencapai kampus G ya. Kampus G kan di akses UI, berdekatan dengan resto cepat saji itu ya. Jadi kalau kita mau mencapai kampus G misalnya kita bisa melalui beberapa cara, misalnya lewat jalan Margonda, bisa lewat jalan RTM, bisa lewat Cijantung, atau bisa lewat akses UI. Nah, kalau menurut hukum Hess, seharusnya besaran total perubahan energi itu sama. Tidak tergantung pada rute mana yang kita pilih untuk mencapai kampus G. Kurang lebih begitu. Ini saya kira untuk pertemuan pertama kita. Ada yang mau bertanya atau ada yang ingin dibahas dalam pertemuan pertama ini? Ada? Oke, terima kasih Ferry. Kalau tidak ada, saya akhiri pertemuan pertama kita di mata kuliah Fisika dan Kimia Dasar 2B. Terima kasih banyak atas kehadirannya. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam. Terima kasih Bu.
Sama-sama.